All right, I too have a live demo today with no video recording as a backup. So we'll see if the gods are on our sides today. OK, this talk is going to be the full 25 minutes. And it was originally supposed to be a lightning talk. I might overshoot the target a little bit, so I'll start a timer on my end. But OK, perfect. OK. There we go. Speaker notes are working. Presentation is working. OK, that's perfect. I'll just quickly try and get this. Maybe like this. OK. Yeah. Hello, everyone. First of all, thank you to Takera for hosting. This is really great. I'm Felicitas. I'm the head of research and development at Loophole Labs. And Loophole Labs does live migration of all sorts of workloads for all sorts of use cases. I work on the process migration these days, but we've historically worked on stuff like VM migrations. I've also implemented the first version of the network migration for this product. And yeah, there's going to be some social media, some links at the end. But yeah, let's jump right into it. The first question everyone probably has is, what is checkpoint restore? And the basic thing is that checkpoint restore captures the complete state of an application into a file and allows you to later restore from that file. And when I say the full application state, I really mean everything. I mean stuff like the CPU registers. I mean stuff like the memory content of a process you're snapshotting. I mean stuff like the devices, even GPUs, for example, or other accelerators, PTYs, TTYs, that kind of stuff. And also, of course, the file descriptors. And yeah, I'm going to be basically introducing what the topic exactly does, what you can use checkpoint restore for. I'm going to be talking about 3 different implementations of checkpoint restore: CRIU, gVisor, and the KVM approach, and how to implement it in Linux. And at the end, I'm going to show you a live demo. Hopefully, we'll see how well that goes. Using it inside of Kubernetes with a product we're developing called Architect. But first of all, I want to talk about some use cases. And the first one, well, it says scale to 0 here, but it was supposed to say amortize startup time. Basically, the idea is that a lot of programming languages, like Python, for example, they require you to read the source files from disk first before you start an application. So it can take quite a while for your application to actually start. Similarly, so for Spring Boot, if anyone's ever worked with Java applications here, I've seen applications, like enterprise applications, take like a minute or so to spin up, which makes them kind of stateful because you can't just turn them on and off again. Stuff's going to break. And for checkpoint restore, it's really nice because you can just start it, create a checkpoint, then restore that checkpoint that's already initialized later on. Basically, you can amortize the entire startup time. Another common use case for it is actually interpreters. So Node.js is actually quite fast, but there's a lot of other runtimes for other languages that just basically need to warm up memory somehow, or need to run some like JIT compilation, all that kind of stuff. All of this takes time and CPU cycles, and with checkpoint restore, you just do it once, start a snapshot, you store something in the future, you can amortize all of that startup time. And another one we've recently run into is actually for LLM inference. There was a very interesting post by Modal a while ago where if you run something like Olama and you load a model for the first time, even if you use mmap to actually load the model, it's still going to take you a significant amount of time, like multiple seconds. And if you want to run a serverless LLM or something like that, that's of course going to be quite a big blocker for you. And with checkpoint restore, with GPU support, you can just checkpoint the entire inference application or training application and then restore it afterwards again. So yeah, that's the first use case, amortizing startup time. The next one is scaling to 0. So basically, the idea is that there's a lot of application types that you don't really need all of the time, like regional websites, like the BC government websites, probably going to be accessed mostly during the day and mostly by people from BC. You don't really have to leave them running for the entire time, 24/7. Also, a lot of architectures scale horizontally quite quickly, but that requires your applications to be super stateless because you need to really spin up instances, shut them down again, which can be kind of suboptimal, especially if you have an existing large code base that's stateful. And yeah, also applications that have varying demand. Like, for example, imagine you have like a lot of users in the morning and a lot of users in the evening. The problems of the cloud kind of force you can just kind of scale it up and down dynamically. But I think most people have realized that that's not really how the cloud works these days, if you have an application of any level of complexity. So yeah, that's basically the idea here. And usually the problem here is that to stop an application, start it again, you have to restart it again. With checkpoint restore, if you checkpoint the application, nothing stays in memory. Everything gets swapped out. The actual resources get released. In the Kubernetes context, that means that your pods are going to have a resource request of 0, and your cluster usage goes down. If you use something like Carpenter or something like a node autoscaler, that means that your actual CPU or your actual nodes will get released back, sold back to AWS, which can then reuse it for other stuff. Then, if new traffic comes in, if you need to scale back up again, you can simply get the nodes from AWS again. The cluster usage goes up, and the nodes will be automatically added back to your cluster. So you can basically kind of automatically right-size your Kubernetes cluster without losing any state and without paying the penalty of restoring it, of restarting an application, which of course means you lose state. You need minutes to spin them back up again. With this, it's just instant. The other big use case of checkpoint restore is actually live migrations. If anyone has ever done like a migration between like physical mainframes and stuff like it, you might notice that moving from one to the other almost always causes downtime. It doesn't matter how smart you're trying to be about like A and B routing or replicas, or in Kubernetes context, something like a max scale request, something like that. And you're probably going to have downtime because when the app moves from here to here, it's going to have to restart. You're not actually moving the app, you're just rescheduling it to a different node, which then causes a restart. And that, of course, has downtime, which means that a move like this usually has some kind of level of cost associated to it, or some kind of risk associated with it. With live migrations, it's a very different story because moving from a node to another node is genuinely just creating a checkpoint on the first node, storing it over there, copying the checkpoint over to the other node, and restoring it. So the entire app state with all of its files, all of its memory, all of its network connections are just going to be restored after the migration. So there's no downtime in the way you would usually think about it. That also allows some pretty interesting and cool use cases. For example, imagine you have a node that you want to take down for maintenance work. You can just live migrate the workloads from one node to another node. You can then perform even physical maintenance, like swapping out a power supply or swapping out a graphics card or something like it. And you can just live migrate back to it. So it basically allows you to do migration work, so to do maintenance work with absolutely no requirements for any downtime, which is quite interesting. And also, of course, this allows some interesting things with bin packing. Like if the cost of you moving is effectively 0, and you happen to have like a small space of compute available on one node, you can simply evacuate your app, move it into just that right spot where you usually wouldn't do it because there's a risk associated with you moving the application or downtime associated with you moving the application. So that is the core use cases of checkpoint restore. Let's try and get a little bit more technical here. The first implementation I want to take a look at is CRIU, and yes, that is the actual logo of the project. CRIU stands for Checkpoint Restore in Userspace. And it's basically a collection of mainline Linux kernel patches and a Userspace program that then interfaces with the exposed kernel interfaces and allows you to dump and restore kernel resources of arbitrary type. And it works in a pretty simple way. Essentially, it starts, and this is going to be, some of these slides are going to be, I try to skip through for time reasons, but essentially what it does is it goes ahead and it seizes a thread, much like GDB does with ptrace. It injects a code snippet into a target process and infects it, so to speak. Then reads all of the memory maps from procfs, so that includes stuff like shared memory regions and stuff like this, and writes into a file. And keep in mind, by seizing a process, you basically pause it, so you pause time completely, so nothing drifts. You then go through all of the file descriptors through those before mentioned mainline kernel patches, and dump them with all of their positions and flags into Userspace. Sorry, just 1 second. And yeah, and the same thing basically happens for all of the kernel resources that could be associated with this process. For example, stuff like network namespaces, like PID namespaces, like child processes, like any other kernel state, any devices, stuff like this. And after that is done, the process can either continue to run or you can just kill it. This allows you to basically create, sorry, just 1 second. I spoke at KubeCon like a week ago and my voice is still kind of gone. After checkpointing, basically you can either leave a process running. That's super useful if you want to create like backups of your application in different timeframes. Or you can just simply completely kill it afterwards, which is what you usually want if you scale them to 0. And on restore, it's a very similar approach. You, first of all, go ahead and you recreate the process skeleton that you have just checkpointed, with just dummy empty processes. Then you, because you want to restore the same PID after a recreate, you basically lock the kernel resource that tells sets the PIDs. you set it basically to like the PID you want -1, and then Linux will automatically give the next process the correct PID that so you can restore it. It then recreates the network namespaces or joins them like the way they were before the checkpoint. For example, if a process finds instead of a container, that's how you get it back into the container. You go ahead, you reopen all of those original file paths, all of those pipes, all of those sockets and TCP connections. You even flush buffers back into the pipes and the TCP connections so that everything gets rehydrated from source to the end. You also remap all of the memory regions, so that includes like mmap files to the original addresses. Some of these, the anonymous regions, are going to be stored in the actual checkpoint file. The actual files themselves, like an mmap file with map async, for example, or map shared, is going to be read directly from the file system one more time. And the same happens with CPU registers, which is actually quite a clever hack, I think. Basically, you restore the CPU registers, including the instruction pointer, restore signal handlers, credentials, so like permissions, all that kind of stuff, like user ID, group ID. And then you just jump to the restored instruction pointer, which basically just resumes it from exactly where it left off. So from the application's perspective, absolutely nothing happened. It just continued running. Time will skip, probably, because you have probably taken a second or two to do this migration. But from everything else, everything keeps on running. Syscalls keep running. The actual calculations you're running concerning files are still open from the processor's perspective. PID is still the same. So stuff just kind of works this way. CRIU is a pretty smart implementation. It has quite a few benefits. The biggest one is this is just processes. You can use this for containers, but at its core, it's just processes. So there's no runtime overhead. There's no virtualization. There's nothing involved there. CRIU also has checkpoints that are somewhat portable. So as long as you are like within roughly the same CPU, you can't use this to migrate from like x86 to ARM, for example. But you can use it to migrate from like a 5th generation Intel CPU to a 7th generation Intel CPU, and sometimes AMD Intel. It depends on what you're doing exactly, as long as the instructions are there, of course. And also, something to keep in mind, that is, of course, the cost you pay for this. This is quite a complex process. There are thousands of kernel interfaces being added to the Linux kernel every single day. And there's 10 people making sure that they all get checkpointed. So, of course, you are going to be on the losing side of this battle most of the time. But for most custom applications, like a Java app, a Go app, a C app, it doesn't really matter. If you're using a normal set of the kernel features, it's a good chance that you're going to be able to checkpoint it with just CRIU. Yeah, basically the whole story here is this needs a lot of careful instrumentation to work properly, a lot of oversight. gVisor is a fundamentally different approach here. It provides real sandboxing support. So it actually sandboxes your application, and it virtualizes syscalls, file systems, and networking. And I'm getting a little bit into a time crunch here, so I might skip a few steps in the next explanations. gVisor is completely different from how CRIU does it. When it starts a process, it first of all works on a container level, so it reads the OCI runtime spec, like C run or run C would. It creates a new process in a sandbox, a new skeleton process again, configures network namespaces and all of this kind of stuff. It then starts a new process called a gopher. It's basically a file system proxy that has very limited capabilities, so no capsys admin, just stuff that has to do to like read and write files. And it spawns something called the sentry, which is a sandbox component. And that is basically what the fork process morphs into. After that's done, it sets up its own kernel. So this is still running on Linux, but it renders its own user space kernel, kind of like how microkernel does it. It mounts the embedded file systems via the sentry component. And it sets up NetStack, which is a full implementation of the entire Linux stack, Linux network stack, like TCP, UDP, QUIC, all those kind of protocols in Userspace. And it basically exposes them to that guest kernel as though it was the Linux kernel implementation to virtualize things. And most importantly, it uses Linux seccomp filters. So for those who might not be aware, seccomp is what allows you to restrict which syscalls a process can do on a sentry. It's only about 40 or so. And basically, this allows the sandbox to only do a very limited set of syscalls, like read and write, but not exec. So you can actually sandbox the process itself properly. And then it loads the container binary into PID1, memory mappings, all that kind of stuff. And it creates an init task in the container. So that's where the memory, etc., gets connected. And basically just unblocks a channel, and it restores. That's basically how gVisor works. It's kind of in between a virtual machine and a normal process that you might be used to. Now you might be wondering, how do things work in this kind of strange setup? So I've added a few examples. If you're doing a syscall, for example, that gets called by something called a platform. That can be something like KVM. It can also be something like systrace or ptrap. You can kind of swap those out. And then the implementations of those quote-unquote Linux syscalls get emulated in Userspace by Sentry. Like a read request, for example, will get sent through the Gopher. And actually, that's the next one here. If you do a file system I/O, for example, that gets called by a virtual file system layer, which then gets resolved by an RPC to that local sandbox Gopher process. And for network I/O, it's also similar. It doesn't go directly to the kernel. It instead goes to our Userspace implementation of TCP and the entire device API, written in Golang, which then just writes it on the host with, again, its sandbox component to an AF packet socket. That's a raw packet socket, not like a TCP socket you might be familiar with. That's basically how gVisor does its process starts. And that gives us very cool features for checkpoint restore. Because for the checkpoint, we can do something completely different this time. We get a request, a sandbox control socket. I'm not sure, has anyone here worked on an OCI runtime before? Probably not. But basically, that's a component that Kubernetes calls out to actually start the container in the end. It's kind of like how the CNI, like Calico is, I think, a CNI, if I understand correctly. This is the compute equivalent of the same thing. It gets a request to actually do a checkpoint. It pauses the internal tasks by sending an internal 6-stop signal. This doesn't actually get sent to the process itself, of course. Stops off the timers. Basically, it can pause time from the process perspective so that nothing drifts. We get a consistent state of snapshot. It flashes everything, and then it starts just serializing objects. gVisor's kernel is written in Golang, so you can just basically call the equivalent of like JSON.stringify on it. Of course, in Go would be a Marshall, but same concept. You just stringify every single component, the registers, the memory, CPU registers, credentials, and so on. Same for memory, so you dump the process's memory, which is also managed in Userspace by this Go process. You serialize the file system state, so that's like where files are mounted to and so on. You do the same thing for network space. Again, it's all Userspace, so it's very simple. You just dump the Go things into a JSON file and you're good. And then eventually you take a look at something like a terminal. So terminals are also emulated. That's if you run like an exec command in Kubernetes, for example, or like a Docker exec command. And eventually you write everything into a checkpoint file. So it's a mixture of protocol buffers, its own format, and some JSON in there, basically whichever one is most efficient. And this, of course, has quite a few bits. Yeah, of course. Afterwards, you can also kill it or keep it running, depending on what your use case is for checkpoint restore. Has a lot of benefits over just running a process. The biggest one probably is that there's no need for PID emulation. The whole jump where we have to change the kernel's current PID and then set it back. We don't have to do that anymore because we in Userspace actually control the PIDs. We don't need to infect any processes because we just spawn from the outside and we can do the actual checkpointing and restoring from within the sandbox, not from within the actual process. And we can go ahead and we can make the TCP checkpoint restore much easier because we control the entire network stack and we don't have to worry about the kernel doing something. And similarly, so the restore process is basically the same thing but in reverse. So first of all, we go ahead, we create our sandbox process again, our skeleton, and I just jump through this a little bit. We read our memory files. We parse where they have to go to. We basically iterate through the tasks, much like we iterated through the process skeleton earlier. We set CPU registers and signal handlers. We create our memory managers again. We actually reopen files. That's the difference between CRIU and here. The file descriptors won't stay open because we can actually make virtual file descriptors. Then we just reopen the files after checkpoint and pretend that they're the same ones as earlier. Same thing, yeah, exactly for file descriptors. And same thing for network state. We just rehydrate the devices. We create the devices with the exact same MAC address and IP address and so on that we did before the checkpoint. Same with Unix sockets and devices. And eventually, we will just simply clear a flag, and we resume time, and we pretend that nothing happened. The end result of this, exact same thing as before. Process gets checkpointed and restored completely transparently from the perspective of the actual process itself. Now, that is the gVisor implementation. And let me just quickly jump through my notes here. Yeah, we're getting a bit tight on time. For Firecracker, that's the last option. It's a full-on VM snapshot. Some people might be aware of VMware's vMotion, for example. That's how those things are kind of implemented. Of course, KVM in this case. And there we start a MicroVM, like an actual virtual machine, not a process. We use KVM for the isolation, not our own Userspace sandbox, or just nothing in the case of CRU. Of course, that gives us a certain level of overhead because our guest kernel now exists. There's a host kernel and a guest kernel. Those both have to allocate resources. But we get some benefits as well because we can actually control how the virtual CPU looks like by setting a CPU ID and so on. And of course, a big requirement here is that you now need hardware acceleration or nested virtualization. So you can't run something like this on top of EC2 by default. You need an actual physical machine or nested virtualization. And I don't think I can jump through all of this. If anyone's interested in how MicroVMs work later, I have the entire thing in here, and I'll also be linking these things on the docs. But with MicroVMs, basically the way the code paths work is code runs on a physical CPU, but is sandboxed via VTD and VTX in the case of Intel and AMD. Devices are implemented as virtual drivers in the guest OS with Vireo, then get implemented on the host. And networking happens with tab devices and network namespaces, kind of similar to how gVisor works, but a bit different because we actually use a guest kernel with proper C implementations of those interfaces. And the checkpoint restore thing, again, I don't have enough time for it, but it's conceptually quite similar, except this time we dump almost like a physical machine. We basically look at the RAM, we write a RAM to disk. We look at the CPU registers, we write a CPU register to disk. It's a bit different in this one regard. Of course, this is a lot easier here because we control the entire CPU, all of the devices. We don't need to restore TCP connections because we work on a device level. We just restore a NIC. We don't restore individual connections. And we don't need a virtual file system because there's no file system. There's just block devices. It's like a physical drive that we plug in and out. And yeah, of course, we get some nice things as well because we can basically lazy load RAM allows us to do very efficient restores of this kind of stuff. And yeah, I'll also be skipping the MicroVM restore logic because we don't have enough time for it. The last thing I want to talk about today is PVM, a page table virtual machine. Some very interesting patches from Alibaba that have been making its way into the Linux kernel mailing list recently. The basic thing is that VMs need a vendor implementation. That's why they can only run on bare metal or on nested virtualization. So you have to opt in as a cloud provider. You have to opt in as an end user to use this. And emulation is always an option, but it's really slow and there's a lot of latency. So you don't want to use emulation for any kind of production workload. And of course, nested virtualization also has high latency because now you're jumping through multiple kernels to get everything to work, and it's just very slow. PVM, and this is if you want to scan it, this is the actual patches that were submitted a while ago. This basically creates an implementation of the whole KVM vendor system in Userspace. So in this case, and no worries, I have this linked in the end again. Basically, the guest kernel runs in ring 3, like any other Userspace process. So you just use software flags and a software page table to enforce isolation. Syscalls have a new in-kernel switcher that works. So no need to jump to VTD or anything like that anymore. It just all runs in Userspace. Hypercalls work in a similar way. And the shadow page tables basically function as a sort of software MMU. So instead of using the CPU's hardware emulation features, you just do this in a very efficient way directly in the host kernel. And interrupts also have some smart handling logic so that they don't take up a lot of cycles to work. This is very fast, actually, for CPU-1 processes. So if you run a calculation or something, or you run some experiment, this is going to be faster than actually using a vendor implementation because it's just a process. But it's going to be slower if you do a lot of forking. Imagine a Linux kernel compile where you spawn 30 or 40 make or CC processes. So it kind of depends on your workload. And also, very important, this is not mainlined yet. We maintain our own patches for this at the moment. And I'm going to be linking at the end. But this is not something you can use just on EC2 or something just yet without a lot of hacking. The last one I can't talk about, not enough time for it. If anyone wants to know about it more later. We also do this for network migrations. So usually networking breaks. We have found a way to skip this by running special code on the network cards. Again, there's a blog post on this. I'll talk a bit more about it later. And basically, we intercept traffic. We buffer it before a checkpoint. We do a checkpoint. We restore a checkpoint. We then flash those buffers back into the devices. We unpause the connection. And as a way, we can basically skip the basically do migration from one node to another node without anyone knowing that the migration happened. Not even you as a client knows it. So it's completely server downtime. And I've got 2 minutes for the demo, so let's see how well this works. And basically, I'm going to show you how checkpoint restore works in Kubernetes with Architect. And let me just quickly add this over here. OK, there we go. I hope the audio is still a little bit usable. I shall clone this screen. OK, there we go. So I have opened up a console. This is currently in technical preview, but this will be the same experience if you're using it once this is an actual product. I'm just going to call this CNCF-Vancouver. And I've already prepared I don't have an internet connection. That is because I don't have a hotspot. Just 1 second. And we should know more in just a bit. There we go. And please give me an IP address. I'll try it again. It's not working yet. Why is it not working yet? There we go. So I'm just going to create a new cluster. We're going to get a nice Helm install command. So Helm is the package manager used for Kubernetes. Oh, 10 more minutes. OK, thank you. That's very nice. So basically what we're going to do now is we're going to install a piece of software to an existing, completely clean Kubernetes cluster. And we have a little license key in here and all that kind of stuff. And I'm just going to quickly paste this in here. There we go. And what is happening, I'll use KNS. It's a very nice terminal UI you can basically use to inspect how your Kubernetes cluster is doing. And what you will see in here is that there's going to be three components with two replicas in one case. There's a control plane, there's a manager component, and there's a daemon that runs on each, or daemon set that runs on each node that we have labeled in a special way. It's going to take about 20 seconds. And again, this is a completely clean Kubernetes cluster. And we can see here it's initializing. There we go. We now have two new runtimes that we can use. There's one called runC architect, one is called runSC architect. runC, that's just CRIU. runSC, that is gVisor. And now we can basically use those, just like we would use something like Kata containers or runC or whatever we want to use. And it's super, super simple. I have prepared a example application in Go that we can use to test whether memory sampling works. And it's the world's dumbest HTTP server. It literally just has an endpoint here called, let me see. And yes, it does panic in the main routine. That is actually intentional here. So all of this does is it has two endpoints. One is called get, one of them is called post. Memory, of course. And we basically just read a request, write it into a memory variable, and we return it back again on the get endpoint. So this, if you usually do a migration or stop it, it would get deleted because the new process does not have the same memory anymore. But with checkpoint restore, this will actually keep the memory alive. So what I'm going to do in here is I'm going to install this example application. And again, it's just a simple Helm install, but you could use any other app as well here, of course. And we should see this get scheduled in just a little bit. And there we go, pod initializing. Let's see. All right, and in here we can see that the runtime class name for this is just runC architect. And there's some new labels in here that you might not have seen in Kubernetes before. You have something called a status in here, for example. You have something called scale down durations and a few other helper annotations. Now the default here is 10 seconds. After 10 seconds of inactivity, this app is going to scale down, hopefully. There we go. So the app has just scaled down. Now, in order to scale it back up, there's a few things you can do. You can either send network traffic. That's going to automatically wake it back up from its checkpoint state. Or you can exec into it. I'm going to use the exec method. And I have prepared a little Linux program here that we can use if I can find where I stored it. There we go. And what this tool basically does is it just looks at all of the resources we have across the entire cluster. So this is like the 4 nodes, all of their memory and RAM usages and so on. Now, as you can see right now, it's just a steady line. If I go ahead and I exec into this container, you will see that, voila, we get a spike in the CPU usage. So we now use 22 instead of 19%. And similarly, so if I exec into the second one, you will see that the users once again goes up. So like restoring a checkpoint actually increases your cluster CPU usage. And we can also see this in here. It says running. And on here, the resources are currently probably at 0, which they should be. Actually, we're too slow. 10 seconds have passed, and it has scaled back down again afterwards. So if there were activity now, it would be scaled up. But basically, this is how it works. There we go. Requests are currently back to 0. So it has scaled down. It has released its resources again. And I'm just going to quickly go in here. I'm going to spin up one of these, and I'll start a port forwarding to my local system. And I will just simply use our little endpoint to post some data into it. I'm just going to store, oh no, what have I done? Port forwarding failed. Lost connection to pod. Okay. Let's try again. There we go. So I've just stored the variable train in memory. And of course, if I try and get this again, we get it back. So this is what you expect to happen. Now, usually, if I were to now delete this pod and recreate it somewhere, that state would be gone. But because we have live migration support, if you just delete this pod, it will, of course, get recreated by the relevant deployment controller. And you can see in here, it has scaled down. We will also see some events down here. We will see down on the checkpoint, claim checkpoint, all that kind of stuff. So it has basically not created a fresh container. It has actually just migrated in the old state. And if I go back in and I spin up this container again, and I start my port forwarding again from the example go1, like so, and I get my state again, you will see that, voila, even though we have just physically moved between two different Kubernetes nodes, by deleting the pod and recreating the pod, memory state actually stays completely intact. So we've basically done a live migration of a regular old Kubernetes pod with no custom code. It was just swapping out a runtime class and adding a few annotations, and that was the entire thing that we had to do. And that concludes my demo. I shall quickly jump back into the shared screen mode to, let's see, my mouse pointer is over there. And voila, let's jump to the very end really quickly. A lot of slides. So yes, if you want to try this out yourself, this is currently in technical preview. We did the first preview of this at KubeCon 2023, one 2024, and another one at the last KubeCon. But this time it's actually happening. The dashboard is live. You can actually install it. It is currently behind a wait list. So you'll have to sign up. You'll have to give some extra information. We will give you a white gloves approach to trying it out. It is also currently completely free. So if you have a home lab, you can try this out on there. And yeah, if you're interested, there's a link to the waitlist on the bottom left here. All of these slides, all of the extra information is all in the right link. It's all on GitHub. And yeah, also some social media if you're interested in more Linux kernel hacking stuff or more virtualization stuff. And yeah, thank you for listening. Yes.
I have a question. You know, it would be tricky to leave, not to explain to me because it is going to, I would be left in chaos, right? So you mentioned checkpoint stuff in the user space, right?
Yes.
You mentioned XDP for eBPF, right? You mentioned architect. And so like, what I'm interested in, you know, first question, you know, like, did I understand well, you know, like that, basically when you create a checkpoint, essentially, you know, you do like some kind of, you know, scaling down. And when you restore that somewhere else, it basically scales out. So that's the first question. The second question is, you have that eBPF, right, stuff. And so let's say you have the Calico stuff, because the guy's here, right?
Mm-hmm.
And so, like, I believe, you know, like, there is a blend of when the eBPF is being configured in the kernel. So basically, IP tables are not in the user space. And so when you do this, like, create checkpoint, is it going to kind of, you know, like, create a snapshot, the full snapshot of the custom kernel? And so when you do the restore, then basically the restore or some other place is going to, everything that existed in that custom kernel is going to be replicated, but like in the user space. So these are two questions.
The first one, yes, exactly. That's exactly what happens. You restore a checkpoint, and it scales back up, so it reuses the resources. It's actually configurable. I'll just quickly get this out of here. It's actually configurable. So if you don't want them to scale back up after migration, you can also wait until there's more network traffic or an extra command, and then you scale back up. That's how you can prevent a thundering herd during your migration. Otherwise, every time you migrate, you would spin up a whole bunch of extra resources, need extra nodes, and so on. The second question, it depends on the way you do it. With this specific version, so XDP stands for Express Data Path, for those who don't know. And basically, it means that traffic that gets sent to a node that has XDP enabled doesn't actually make it into the kernel. Or it makes it into the kernel, but not to the entire network stack. Instead, we take the traffic directly from basically the second it comes off the network device and then do stuff with it. So this will actually work with any CNI you can use. It works with Calico, it works with Cilium, it works with anything you want to use, even Flanell, even like layer 2 ones. It's completely independent of the CNI system. That's for process migration for VMs, and we actually did a talk at KubeCon 2023. If you Google my name, you will find a video about it. There's two ones actually. For those, actually, we migrated an entire Kubernetes cluster. So we migrated the kubelet as well. We migrated the network plugin, all of that kind of stuff. It just depends on the level of abstraction that you would like for your specific use case. But yeah, it's totally up to you. This version migrates just the process and make sure that the state of network connections and everything else gets over. But we can also do the entire cluster if you like. Yeah. Any other questions? Yes, Sadie?
So how feasible is it to include like GPU state? You said devices are included. So what's
Yes. So there's two things to that. So there's the ways I can do it. AMD GPU. The first one is virtualization. Using something like Virtual GPU already works. So if you have, like, for example, that Virtual GPU implements a virtual GPU in the guest using the Vulkan acceleration of the host GPU. Basically, that allows you to serialize the entire CPU state, which is GPU state, which is kind of nice. That one, however, is very not very performant, and you can't use it for like LLM inference, for example. For AMD GPUs and for NVIDIA GPUs, there are now specific plugins for CRIU or CRIU that allow you to checkpoint that state based on basically the driver exposing the GPU internal memory state to the kernel. Very complex, very fragile. What we are currently working on with Nicholas, who actually did this as his PhD, is we have basically implemented a CUDA level interception library that can forward RPCs from the CUDA program to the actual CUDA GPU on a remote instance. So you can actually run the GPU on the host, and you can then mount, quote unquote, the GPU on the guest completely transparently. It uses Virtual VSOC, so it's very, very fast. It uses a shared memory region, doesn't actually have to serialize anything. But that means you can just record a log and just replay it afterwards. And because GPUs are fully deterministic, that means you can effectively live migrate them and then whole model from A to B whenever you want to. Yeah. More of this in KubeCon Europe in Amsterdam next year. It's going to be a live demo of that. Yeah.
Can you checkpoint distributed application space too?
Yes, you can checkpoint absolutely anything. We have previously done this in coordination. So the KubeCon 2024 talk is very interesting on this. I took a K3S cluster with 3 nodes, and I migrated one node from Chicago to Frankfurt. I migrated one node from Frankfurt to Chicago the other way, and I migrated another one from New York to Chicago, all at the same time, and it just kind of works. Again, we have support for migrating anything you want to. As long as it runs on Linux, we're fine. Yeah.
My concern is not necessarily not strictly migration, but I'm thinking that an application has its state split between 2 different nodes, and you need to restore them both at the same time and take the checkpoint at the same time. I was thinking, is this robust enough to support that, or?
It kind of depends. So as long as you include them in the checkpoints at the same time, of course there's like clock drifts involved at some point, right? We don't usually recommend doing this. You can. In Kubernetes, it's very easy because Kubernetes will just reconnect in case stuff fails, and it will eventually reconcile the state for us, right? For something like, we also use this for Redis and Postgres databases, like sharded databases. That works very well as well. We also use this for serverless Postgres, for example. So if you want to like run Postgres and you only want to have the server up and running when actually it's actually servicing requests, that actually works really, really well. But the network layer, depending on how far you opt into the stack, has to be either be able to repair it, or you have to accept an additional hop. That has to happen at some point. Yeah.
So the architect is basically your homegrown software, right?
Yes, the architect is basically everything I showed you in like one nice user interface. It is, do I still have it open? I don't have it open anymore. But it was the terminal. It was the web interface I showed you earlier, the console basically.
And how is that different than eBPF XDP?
The eBPF stuff is just network migration. It's just part of it.
So it's just migration, right?
Yeah, just network migration. We have an interesting blog post on this. It's just this one here. We managed to, like, usually in Userspace, you get up to like 2 gigabits per second or something. With this, we got like 200, and we're currently testing it up to 800 gigabits in a server that's just across Falls Creek. So probably going to be another blog post pretty soon about that. Yeah.
Great.
All right. Well, thank you, everyone. And if any more questions, feel free to come to me.